Well, thank you very much for your introduction, Professor Tenne. The first comment I want to make is I come from a small country. It's called Scotland, and it rides on the back of one that's been, for centuries, 9 times its size. The fact that the one that's 9 times its size is misbehaving at the moment is a source of, I think, some anxiety for my small country. You have also the privilege of being a small country, much younger than the one I come from. But I think the commonality between the two is that both have punched very much bigger and higher than their weight or their size. So congratulations on making it for 70 years with such a spectacular output, certainly in the sciences. Well, what I want to do is, first of all, talk about the creation of the mechanical bond. And in doing this, I just want to point out at the beginning that if we consider chemistry, then, I don't know, 1,000, 2,000, 10,000, 20,000 new compounds being produced every day. Maybe in a whole year, there might be a few new reactions described, but it's only once in a blue moon that you have a new bond. It's the mechanical bond that I'm going to talk about. That has the strength of the weakest covalent bond that participates in the molecule. But before we go there, I want to put our research in context by going through engines through the ages. And where would you start? No better than with the wheel. This spoke wheel we're looking at is over 4,000 years old, discovered in what we now call Iran. And the wheel is one of the so-called simple machines, the others being the lever, the pulley, the screw, the wedge, and the inclined plane. So after mentioning that, let's go forward to only about 300 years ago, when steam came on the scene, followed by electricity, electrical motors, then internal combustion engines, then diesel, then jet engines, then rockets. And then we'll step back a little, and of course this is a segue back into what Rudy has been talking about, biological motors. And then finally, where my heart lives, with these molecular motors. And of course, I'm not going to say this is the end. I leave you to think what could come next. So going to steam engines, I guess a fellow Scot, James Watt, was very early in the game. Here we see in 1765, one of his early conventions, or inventions, I should say. A little later here, in 1883, this is one from a company in Pennsylvania that was used to drill oil. Soon they took these engines to wheels, and we have trains. And I single out from 1829 the so-called Stephenson's rocket, which you can see in the Science Museum in London. It was one of the first to ply between Liverpool and Manchester. And then back playing up to my Scottishness, there's the 1923 variety of the Flying Scotsman, which took the journey from Edinburgh to London down to 6 hours. And then going across the west coast here in Oregon, you see this train, which is still plying back and forth up and down the coast today, with tourists, of course. Electrical motors. So where did they start? Well, Faraday, back in 1821, demonstrated, probably for the first time, the conversion of electricity into mechanical energy. But it was a Hungarian, János Jedek, and we'll come back to him later, who created the first, if you like, electrical motor. And this one that we're looking at is still working to this day. Here's a variety of one that was actually a gift to Lord Kelvin from James Joule. And then fast forward, of course, we're using them in our homes and on our roads every day. And then look at this one. There are some 60 cities, I'm told, bigger than New York in China, that are now linked by
The Beijing to Shanghai high-speed train has even clocked in speeds up to 480 kilometers an hour. That's about 300 miles an hour.
I don't know if we can tone this noise down a little bit, but you got the message that they have these trains between these big cities that are just awesome. Internal combustion engine. Here is, in fact, a patent of a German Otto Langen of a gas engine, which, of course, made its way through into the well-known combustion engines that supported the Ford T. 1908 through to 1907, there were almost 17 million of these brought onto the market. And then in a more light-hearted vein, here's Fraser Stoddart's 2011 Toyota, which has a very privileged place to sit when I'm in my office. The diesel engine came, and I learned something in putting this talk together, and that is that it's after a man itself. I didn't realize this, Rudolf Diesel. And there is his first entry onto the scene in 1893. And in much more recent times, they are vast. This one is over, in its generation of power, 100 horsepower, making its way into a cargo ship somewhere. Jet engines. Inevitably, you associate the name of Sir Frank Whittle with the invention of the jet engine. And then here we see Lockheed Martin's F-22 Raptor taking off. And at the same time, we see this passenger jet coming into Heathrow from Perth in Australia, having flown 9,000 miles in 17 hours. Quite a record. And then here's something that I find mind-boggling. At any one instance, there are 12,000 of these contraptions in the air at any one time. And if we put a couple of hundred people in each, then we are talking about 2.5 million people sitting up there in the sky. Believe it, amazing. Rocket engines. Well, the introduction here is not so pleasant, of course, because here we have the V2 rockets that were used by the German military against London and Antwerp and Liège, and of course a lot of people lost their lives. But on a more positive note, come 1969, we have Apollo 11 with Neil Armstrong and Bud Aldrin, and then another connection to my past. Here's the first British astronaut whom I had the good fortune to be her organic chemistry tutor when I was at Sheffield University. That's Helen Sharman, and she took to space in 1991, courtesy of the Russian Soyuz TM-12 Mir space mission, and she was up there for 8 days. And then finally, here you see a rocket actually landing. This is the Falcon Heavy by SpaceX. And then, of course, we've heard in great authority about biological motors from Rudy, and I just therefore mention the walking one that he didn't show us a picture of. Here we see myosin and actin, which of course are also making our muscles work. And if I use the ATP, and I must say I'm very saddened, Shimon, to hear that Paul Boyer passed away, because he was going to be, I think, 100 in, he's 99, but he was going to be 100 in a few days' time in July. So here we see the ATPase. In this case, I'm going to use it to generate ATP to drive the linear motors, which, as I say, are in our muscles. And here we can demonstrate it by going to Wimbledon in 2016. And, can you do anything about reducing the noise. So we saw Serena Williams win the women's single, and now Fraser Stoddart and Murray winning the men's single. All right, so enough of that. Bond, if we take the noun, means different things to different people. As chemists, we don't have a monopoly on the definition. Financiers use it, biologists use it, social scientists use it, anthropologists use it. And if we put the adjective in mechanical in front of it, it's replete through nature, art, architecture, and you can even meet it in the cinema. So we're going back to molecules now. And in order to create the mechanical bond, we had to live in this world of what we call supramolecular chemistry, where molecular recognition, self-assembly, template-directed synthesis ultimately are the order of the day. And so you see the constructs that we're aiming towards, namely going from a complex that you see on the left-hand side there, and I call it pseudoretaxane, that is going to be the precursor to either a retaxane or a catenane. And if we look at these two, and I call them, much based on the encouragement of Omar Yagi, to abbreviate things to free letters, particularly putting a vowel in the middle, to MIMS, mechanically interlocked molecules, of which the two that we know best of all are the retaxane, derived the word from Latin, and catenane, also derived from Latin. The most important point here, though, is that they are molecules. We're back into the molecular world. Okay, so with that introduction, let's use establishing molecular recognition to take us into template-directed synthesis to make catenanes and retaxanes, and then look at their properties in terms of shape change, and look at shuttles and then switches. We go from degeneracy to non-degeneracy. And then going up the hill, because neither of a shuttle or a switch is anywhere near a machine, to the design of an artificial machine, and the one I'm going to talk about today is a molecular pump. And that inevitably takes us towards doing chemistry away from equilibrium. And towards the end, I just want to make the point that, fortunately, scientific discovery is not yet predictable, and probably nor should it be. So establishing the molecular recognition. So this was really a great gift to me. I was not having a very happy time in my first era as an academic at the University of Sheffield. Without going into any details, it was made possible for me to have a period of secondment at Imperial Chemical Industries. And so I go there, and in a roundabout way, I meet up with paraquat, a weed killer, also known as methylvalinogen. And I find that this has great potential as a building block for making mechanically interlocked molecules, particularly if I match it up with this dioxynaphthalene derivative. And so the story goes that by the mid-80s, having left ICI and returned to academia, we had put blue into red, namely paraquat, inside a crown ether, which had been described much earlier by Don Cram for other purposes. There was then the challenge of could we make something that was blue, that was electron deficient, red being electron rich, that would allow us to ultimately bring the two components together. That was actually quite a challenge. And we had to work out how to template the formation of that, what became known as that little blue box. I don't have time to go there today, but we'll just use that templation phenomenon with the synthesis of our first donor acceptor, catenane. And so this, I think, was the most stunning chemical reaction. I think looking back on it, and I don't want to sound arrogant here, a beautiful piece of organic synthesis, not designed, but just presented to us on a plate. So that dication you see up in the top left-hand corner doesn't speak to the red ring at all, which is present in 3 molar equivalents. But in the presence of that dibromide, you form a covalent bond, a nitrogen-carbon bond. You switch on a bipyridinium unit similar to paraquat. And we had proved that paraquat loves to sit inside this red ring. And so we can forecast that it worms its way inside. It picks up non-covalent bonding interactions. In time, we learned that, it wasn't donor-acceptor interactions that were driving the day. It was mainly CHO interactions between the alpha protons on the pyridinium rings and the ethereal oxygens. A little bit, not much, from CH pi interactions, which we'll come to later. And really what was amazing about this was first experiment, 70% yield, crystals in front of our eyes. And given crystals, we could do a crystal structure, courtesy of our crystallographer. And again, what was exciting here was that these two rings weren't sitting with respect to each other willy-nilly, they were talking to each other. And so if we start up there with that Angevin space-filling image in the northeast and go down to the southwest, in 3.5 angstrom planar steps, we have acceptor-donor, talking to each other. And what's more, if you use spectroscopic means, particularly NMR, you can uncover 3 motions. So there's this rocking one, which is actually just breaking, for the most part, some hydrogen bonds and CH pi interactions. But then there is a pirouettic one, where the red ring, of course, what happens anti-clockwise also happens clockwise. We have no control over that. And then finally, circumrotation, which is happening 30 times a second. Now, this is the motion that led, ultimately, when I went to UCLA, to have a fine and very enjoyable collaboration with Jim Heath at the back there, establishing what I think was a big contribution to molecular electronics. And that was made possible by Jim. Thank you, Jim. So what we could do in terms of making a catenane, we thought, well, we should be able to do this very similar sort of piece of synthesis to make a ritaxane. And so using the same principle, and I'll go fast now, the template, of course, is not as pre-organized in the lingo of Donald Cram, and so one might expect, hopefully, to get the product, but with some maybe less efficiency, and that was the outcome. About half the efficiency of the synthesis of the catenane, first time round. All of these have been much improved, and both of them are literally quantitative now. All right, so that's the making part of it. What could we do with these then, having made them? And so, if you allow me, and of course this is giving me a lot of license, just to stretch them out, then it allows me to show you that we have a molecular shuttle. And this ring is going back and forward in a degenerate way. It's just like the chair flip of cyclohexane. But this time it's going 2,000 times a second, a little bit slower, a barrier of about 13 kilocalories per mole. And what I want to point out here is when it was published in JAPS as a communication, I had to fight to keep the last few sentences where molecular machines were mentioned for the first time. It was the then editor, I was told it was hype. So there are times when you've got to stick to your guns and say, no, this is not hype, this is for real. But could we do better? Yes, we could. The next thing was to remove the degeneracy and put in place now a couple of different, what we call stations. So the hydroquinones are replaced on the right-hand side by an electron-rich biphenol, but by an even more electron-rich green unit, a benzidine, on the left-hand side. And we rightly predicted that the blue box would love to spend more of its time on the green unit than it would on the red unit. But this also gave us entry into our first switch, because we could come along with some acid and we could protonate the benzidine unit. And in the presence of acid, the blue box will sit on the red station all of the time until you come along with some base and remove the protons. Okay, so we've got to a switch, but let me again interject. We're not at a micromotor yet. That's a much bigger hill to climb. And in going in that direction, let's just again bring back the idea of this walking microscopic machine that we have in our bodies, as I say, is helping us with our muscle power. But I want to compare it with the macroscopic one that you see up above, which is a sculpture in wood by a Dutch artist that you see walking across some sands in the Netherlands. And why is it doing that? Well, you can see that it sails, and so it needs some energy from the wind to drive it. And we're very much in a macroscopic world of mechanics where inertia, momentum, friction, and gravity are the order of the day. Whereas the biological motor here is it's a molecule. It's in thermal fluctuation. The Brownian motion are the order of the day. It's constantly moving. The viscous forces, in fact, are dampening its movement, the cell materials. And fellow collaborator Dina Stutmian, physicist up in Maine, has described this process as it's swimming in molasses and walking in a hurricane. Okay, so let's take this comparison a little bit further and look at these energy profiles. So if we're in the mechanical world, and we can look at this starting material, it could be a car or a bicycle, and you want to get from the left-hand valley up to the right-hand one on that picture at the top, then you would just make this machine go over, presumably the lowest point, the col, in these mountains, and you would arrive at your endpoint. Not with either biological machines or the ones that are even smaller, because our ones are down in the really nanometer range. It's all about juggling about with energy wells and transition states. And so let's consider the starting material now to be a collection of molecules, and you raise up the energy level and maybe bring the transition state down. You tip them into this energy well in the middle, and then you do another juggling act. You raise it up, and at the same time, you take the mountain behind it, you raise it so that it can't go back, and the one in the forward direction is brought down, and so it can proceed, or that collection of molecules can proceed. And so how do you express this in terms of synthetic systems? So here you see the two components of this so-called flashing energy ratchet. You see the blue box, and you see a dumbbell. Now, we're not going to be making a retaxane. Both of these so-called stoppers, the green one and the blue one, are sterically, electronically able, in principle, as you see from the movie, to allow the ring to come on and go off. But what we're going to be doing here is directing the direction so that the blue box comes on from the green end, and in so doing, and why does it come? Because of the donor-acceptor interaction between its pi electron deficient bipyridinium units and the pi electron rich dioxynaphthalene units. So here we've got molecular recognition in place. Can we switch that off? Yes, we can. If we come along with electrons and neutralize two of the positive charges and have these bipyridinium units become radical cations, then we switch off the molecular recognition, and at the same time we actually change the shape of this now purple box. It is not so inclined to want to go over the neutral end. We've reduced the coulombic repulsion, and so it's prepared to come off the positive end, and that's what it does. And if we look at this energy profile, we can see that The blue box is going to come over the green end. That's the more easy one for it to transverse. And then in that well, we've got molecular recognition, but we can raise the energy such that we push it off to the right. And in so doing, of course, as I say, we've reduced the positive charge. Okay, so a bit of a, I would say, almost push to our work came by a chance discovery, which was far too late in coming along in 2010. And it was that, because it's sort of counterintuitive, we have a cyclophane with 4 positive charges, we have a viologen derivative with 2. Would they ever want to nestle together? And it wasn't a synthetic chemist, it was Elie Trabulsi, a physical chemist, who had the gall to put this couple into an inert atmosphere in solution and show, amazingly, that if you take them all down to radical cations, you get a very strong complex. Of course, all has to be done in a glove box, but of course, when you oxidize and air is sufficient, then you release a huge amount of coulombic energy. And so this is a thought experiment. If we just turn our dumbbell around 180 degrees and put the charged end there on the left-hand side and the neutral one on the right-hand side, it's conceivable now that we can have an energy ratchet that operates in the opposite way. And we showed that it did. But I have to go fast forward in the interest of time. And so this led to the design of a molecular pump blueprint. Now, the point I should have made about the energy ratchet is you pick a ring out of solution, you move it across this dumbbell, and you plonk it back down into solution. You don't do any work. In order to demonstrate that you do work, we've had to stop the ring escaping back into solution. So this is where this design of a pump with the left-hand portion being what you've seen already to some extent, and the right-hand portion being working from the very right, a big stopper to stop the ring going out into solution, a long chain to be able to collect 1 or 2 of these, and very importantly, a steric barrier, or what I've started to call a speed bump. And this speed bump is important because if you're watching this movie that's going on, you'll see that when you do a reduction to bring the ring on from solution, the one that's on the collecting chain wants to come back, and so you've got to stop it. So it's a very much daunting task to design a molecule that behaves in this way. And if one can, then the sequence of reduce, oxidize, thermal energy to get the ring over the speed bump, and then a repetition of this would get us from 1 ring to 2 rings, from a 2-rataxane to a 3-rataxane. So now we're doing chemistry away from equilibrium. Here's the chemical constitution of the actual molecule itself. I would say that probably 50 were made in order to get to this one that behaves rather well. And you'll notice that this NMR work that I'm going to describe has been carried out at 42 degrees centigrade. So we're a little bit above room temperature. And if we carry out the first redox cycle, which is usually carried out with zinc dust, that's removed, and then nitrosyl hexafluorophosphate is used for the reduction, followed by the oxidation. And then we need an hour and a half, roughly, almost, of time for the thermal process to take place for the ring to move over onto the collecting chain. And you can see from these high field signals as they grow that that is happening. And this, as I say, has been repeated. Both the 2 and the 3-rataxane have been well characterized after being isolated. So pumping 1 ring followed by 2 rings takes us away from equilibrium. And in the first ring, we managed to get a 90% yield. The second one goes on with an 85, so overall we have a 77% yield. But the best message from this particular slide is that the energy barrier for the first ring going on is 23, and literally the second one also 23. And so this message is the first ring does not inhibit the passage of the second ring over the speed bump. And so looking forward, and this is what is the grand challenge now, is to put more rings, 1, 2, 3, and then 4. And you'll notice that I'm raising the energy level of this trace to indicate the message that I want to get over to you is that each cycle is trapping a ring in a high energy state. Some of the energy input is trapped, and finally, you have a machine. Work is done. So what do we get out of this? Well, enthalpically and entropically dominated, as they're often called, polyrataxanes. And in quite recent times, we've been tuning these systems so that now we have one that goes through the same process, but now at room temperature, where we've just shifted some methyl groups on a pyridinium ring, and we've taken away a methylene between the bipyridinium unit and the green unit. And that helps to push coulombically the ring over the speed bump. If we extrapolate up to 40 degrees, this is working now compared to the other one in maybe seconds, but probably minutes. And so what we're looking at now is being able to make polyrataxanes using not chemicals, but electricity effectively in electrochemical cells to pump rings onto long polymer chains with molecular pumps at each end of the polymers. And very quickly, here is our latest results, now just appearing in Angle Antichimie, where we've made a dumbbell with a collecting area in the middle. It happens to have, I think, a total of 18 methylene groups and a couple of positive charges. And of course, the positive charges are going to make this collecting area not a very happy one for these positively charged rings. And now we can do the pumping electrochemically, and in so doing, we can have a reduction phase at minus 700 volts, millivolts rather, and then followed by a plus 1.4 volt oxidation phase. And that gives us a free rataxane. We repeat the process, and we can get a 5 rataxane. Now, I think we're coming up to a summary that I'm going to give you, which will allow me to just rest my tongue a little bit, and perhaps you can enjoy what's coming.
Mes plaisirs, je n'ai plus besoin de balayer les amours avec leur trémolo, balayer pour toujours, je repars à zéro. Non, rien de rien, non, je ne regrette rien. Ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien. Ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien. C'est payé. Mes chagrins, mes plaisirs, je n'ai plus besoin de balayer les amours avec leur trémolo, balayer pour toujours. Je repars à zéro. Non, rien de rien. Rien, ni le bien qu'on m'a fait, ni le mal, tout ça m'est bien égal. Non, rien de rien. Non, je ne regrette rien, car ma vie,
Well, I hope that summarizes what I've been telling you, and just remains for me to point out that this is something that's happened over, well, minimally 25 years, probably better to say 50 years, and these are some of the players that have pushed it along. We have brought a fairly big tome, 670 pages, I think. No, 760 pages, I don't do credit, on the nature of the mechanical bond from molecules to machines. Most of the heavy lifting on this was done by a graduate student, but before we get there, it's a 6-chapter book on this topic, introduction that's really written for the layperson, and then 2 on synthesis, kinetic and thermodynamic approaches, molecular topology and architecture, and stereochemistry, which I'm going to make a comment about, and then finally, molecular switches and machines. And here's the graduate student, now assistant professor at the University of Colorado, Carson Bruns. So this whole business of the mechanical bond has completely revolutionized the field of stereochemistry. And so when we were writing the book, we had to invent, on top of what was there already, something like 36 new terms to describe what had been uncovered. And this is not about stereogenic centers, it's more about planes and axes and helices. And here is my pitch. Chemistry is vibrant. It is a new science. And just look at this histogram. Basically, this subject did not take off until the 1990s. Sauvage had described his first catenane in 83, we in 89, and the molecular shuttle in 91. And then it takes off. And notice that ultimately the rotaxanes outbeat the catenanes. Think about that. And then where is it happening? Well, United States, UK, Japan, and of course China will get darker green almost by the day. Leading molecular machinists, well, my 2 co-laureates that were mentioned by my chair, Jean-Pierre Sauvage and Ben Ferenga, and then many others that fill up the space here. And I just want to pick out Ivan Ibrahimian from the Hebrew University, who came and postdoced with me at UCLA and is now at Dartmouth College. Jean-Pierre Sauvage, well, this is one of the machines that he's known for. We call it a C2 daisy chain or umbilical muscle. And then, of course, Ben Feringa has not used the mechanical bond. He's used beautiful molecules with stereochemistry built into them, or particularly a double bond that he can rotate around two components using light and heat. And so, just to sum up, we have steam, electricity, or electric motors rather, internal combustion, diesel, jet, rocket, and let's just go back. What I'm using here is a sort of blue color to indicate nothing was happening up until this time. Then green is the sort of development phase before you see practical application, which is the maroon. Of course, the biological scene, that's been going back to time immemorial, and the yellow represents the knowledge that we've been gaining from round about, I would say, 1950 or thereabouts, 1960. And so where do the molecular artificial machines last? It's very much, I think, fundamental discovery. And where are we going to be in 2 or 3 decades' time? And to put it in context, let's bring back this person in Hungary who introduced us to the the electric motor back in 1827. Was he to know that he would have to wait, if he lived that long, I'm not sure. He did, in fact, 1895, to 1892 to see a fan, and then in 1885, this contraption for mixing milk and eggs and things like that, of which we have much more elegant designs nowadays. So, doing chemistry away from equilibrium, the applications are, I think, awaiting. It's a grand challenge to the young people out there. What I can say is that on the left there, you see slide ring gels. These are an example of an application at the moment that has made its way into scratch-resistant polymers that have been put onto products like cell phones. Here's another example, exemplified last year in a science paper where the silicon microparticles that form in lithium-ion batteries can be, as it were, discouraged from forming by having these slide ring pulleys present. And so that's really my story. I want to thank many people. I'll just come to that finally. But first of all, the many sources of funding over the years. And diversity pays off big time. Science is global. It knows no boundaries. Our group over 50 years has visited 6 universities, coming up as one in Australia at the University of New South Wales. One company where I spent 3 years. We have 2 startup companies. And over the 50 years, roughly 50 different nationalities among 500 graduate students. Amazing. And the final thing I want to do is to appeal to Scottish bard Robbie Burns. We are all one people on earth. Now, this man only lived till he was 37. And he fathered 19 children in that time. But his poetry, and there are more statues to him, incidentally, than any other human being on the planet. His poetry lasts and tells a message that I think is very pertinent to today. Then let us pray that come it may, as come it will for all that sense and worth over all the earth shall have preeminence and all that. For all that and all that is coming yet for all that man to man the world over shall brothers be for all that. Thank you.
Thank you very much, Fraser, for this splendid talk. Questions, comments? Let's start here. Uri, please.
Let's say I want to lift 1 gram for 1 centimeter. Okay, this is the work I want to do. How many molecules of your motors, or how should I connect them to do that work?
Well, I think we'll have to ask Rudy Marcus or somebody to do a calculation along those lines. You know, that's not something that we have considered at this point, but it's obviously going to take many molecules, and if that's the application one's looking for. But I don't think it's a meaningful application, to be honest. I think the applications you're going to see are going to be in chemical synthesis, in material science, and probably ultimately in health science.
I'm curious about, I want to ask about the, the nature of the attraction between these two cation radicals. I mean, they're still, even though they are radicals, they're still positively charged, both of them, right? So what is the force that overcomes the electrostatic attraction? Repulsion.
Well, you've got radical pairing, and in fact, it's a lot more complex than I was able to show in the time available to me. In the tris radical trication, you actually have embedded in there a radical, a bis radical dication, which is effectively looking at a bystander in the form of a radical cation on the other side. Now, whether you call this a sort of resonance or whether you look at it as equilibrium, I would rather look at it as an equilibrium, because we have electrochemical evidence for within that tris radical trication, a bis radical dication with electron pairing, holding the complex, as it were, together, or the binding together of the two components.
Ali, please.
When you draw the one-dimensional free energy surfaces, it could be misleading, because unless you draw it at least in 2 dimensions as a landscape, it's a perpetual motion. You're pushing up and down the energy, which a lot of people in motors are doing. And I think it's important to describe it in the correct dimensionality, so one will see if it has the right directionality.
Yeah, I accept it's an oversimplification, and we should be looking at it in probably multi-dimensions, but certainly 2 dimensions. I agree.
No, but the main point, if you push up and down the energy,
Yep.
unless you have one extra dimension, you cannot really know if it's feasible.
Right, yeah, I get the point.
You sure?
It's pushing the energy up and down, or pushing the coupling up and down. That comes to the relation to what we had from Rudy Marcus, because it looked to me that your fascinating multi-stroke molecular pumps are adiabatic. Now, can one consider non-adiabatic multi-stroke pumps?
Sure.
And then you can change really and control the strength of coupling. You can control time scales.
Yeah, I totally agree. And, you know, these are the future challenges. It's been quite a mountain to climb to get to where we are today. And, you know, as I think Rudy said at the end of his talk, this is a game in progress. And it has to be taken on to larger heights with time. And I hope and I think that will happen. Thank you.
I think we'll, please, one last question.
Could you summarize the efficiency considerations in these engines and these machines?
Again, I can't give you quantitative results. From some earlier motors that we made in collaboration with Vincenzo Bolzani back in the 2000s, about 2005, we calculated the efficiencies to be pretty high. And it was really quite encouraging that the numbers were outstripping those of biological systems. In more recent times, in another type of experiment, we've had results from single molecule AFM, STM type work, where the uncoiling of polyrotaxanes, where there are these interactions not just between the rings and the threads, but between the rings themselves. This experiment has led to outcome that shows that compared with the biological single molecules, namely proteins, the forces involved are considerably larger for the artificial machines, or artificial molecules, I should say.
Okay, I think that point will stop, and if there are any questions or comments.